Hi there, I'm Borna, your organic chemistry tutor, and I'm back today with another solved mechanism problem. Let's get to the board. Alright, this is the mechanism problem I have for you today. You should be able to do this on your own if you have learned about carboxylic acid derivatives, so I'm going to give you a few minutes, pause the video, go ahead and try it, and then come back. Alright, let's see what's going on here. First of all, let me say something. We have a ester functional group in the starting material right here, and then we have an amide functional group in the product right here, and we know that esters are convertible to amides through the use of an amine, which is like what we're using ammonia for, presumably. So I'm thinking, is there reasonable for ammonia to attack this carbon-oxygen bond to open it up, basically do a nucleophilic attack on that carbonyl? So that's what makes sense to happen. And in a second, I'm going to try to see if I can locate the carbons of the starting material in the product and see what connections have been made. Alright, so this is what is reasonable to happen. Now let's see if we can locate the carbons of the starting material in the product. Well, first of all, quite obviously, the aromatic ring has not gone anywhere, so I'm not going to bother numbering that at all. So I'm going to number this 1, I'm going to number this 2, I'm going to number this... Actually, let's go like this. I'm going to go 1, 2, 3, and 4. I'm going to say that it's very likely for 1 to remain connected to the aromatic ring. There's really no reason for that to be disconnected. 4 is probably the carbon of the carbonyl. There is no reason for 2 to be disconnected from 3. And interesting, this is starting to make sense. So what has happened is that for bonds broken, I'm going to use a red to show them in the starting material. For bonds made, I'm going to make use of green. It appears that the bond between the oxygen and 3 has been made, and the bond between oxygen and 4 has been broken. Very interesting. And then on top of that, 3 was connected to a leaving group, Br, and it's no longer in the product. Let's see what we can make of that. Alright, so in order to dissociate this bond, this is basically just a nucleophilic acyl substitution, right? So we added nitrogen to the carbon-oxygen double bond, broke the carbon-oxygen double bond, and now we are left with what we call a tetrahedral intermediate, which is a carbon with an oxygen connected to it, with other groups, including one thing that could act as a leaving group. Now, if we kicked this oxygen out as a leaving group, that is going to give us basically our amide. However, I'm a little iffy about just bringing this down and kicking this oxygen out, because as it stands, NH3+ is a better leaving group than that oxygen because it can leave as an NH3 as opposed to O-. So what I'm going to do is that I'm going to use another ammonia molecule to basically, or actually let me go down. I'm going to use an ammonia molecule to make this NH3+ into an NH2 neutral so that it's no longer a good leaving group. And at that point, our oxygen can come back down and kick out the thing that we want to actually act as a leaving group. Now, let me actually draw the structure of the intermediate that would result from that. It's going to look something like this. So I'm going to have my phenyl right here. I'm going to have this thing with the bromine right here. I'm going to have O-. I'm going to have NH2 right here. And now if the oxygen comes back down, NH2- is a very poor leaving group, so this is the only thing that can actually act as a leaving group, which is great. That's going to leave, and that is going to give us our amide. And as for how the oxygen gets connected to carbon 3, well, that's not very difficult. We demonstrate that in a second. So we have our amide right here. And we have our bromine right here. Now, all that needs to happen for us to get to the product is that this oxygen right here needs to attack this carbon and kick bromine out in an SN2 fashion. However, as it stands, the oxygen and bromine are not kept very close together. So what I'm going to do is that I'm going to rotate this bond, draw an equivalent structure to what I have right now, and that is going to basically looks something like this. So I have that right there, which is great. And then what have I got? I have my amide being a wedge, and I have my phenyl going back. Now, this is the same structure as this one, so the stereochemistry should not change. So to make sure that I did it right, I'm gonna go ahead and determine the R versus S of that stereocenter and see what I've done. Okay, so in that stereocenter, the carbon connected to oxygen is going to be 1. This arrow ring is going to be 2. This is going to be 3, and that is going to be 4. So this is S. It has to remain S. So 1, 2, 3, and it is counterclockwise. It's S. Perfect. I don't need these anymore, so let's erase this. And then all that needs to happen right now is for my oxygen to attack this carbon, kick this out, and that basically gets me to the product, creating a 6-member drink. So this is it.
Alright, I hope you liked this video. If you did, please don't forget to hit the like button. That's going to help me a lot. Also, subscribe to see more solved problems, tips and tricks, and tutorials. See you in the next video. Take care.